Welcome to the boardroom. I'm your strategist, and today we are tearing apart Cambridge A-level physics, specifically focusing on syllabus code 9702, particle physics. We're not just going to casually read through a textbook today. No, we are going to treat your upcoming exam like a high-stakes pitch to a corporate board of examiners. Every single point you make needs to be justified with hard data and airtight strategy. We're zooming all the way down from the macroscopic world right down into the bizarre, fundamental building blocks of the universe, and I'm going to show you exactly how to extract the maximum marks from this incredibly complex topic. Let's get to work. Here is our strategic roadmap for this session. 1. Rutherford's nuclear model. 2. Subatomic particles and isotopes. 3. Understanding radioactive decay. 4. The neutrino mystery. And 5. Leptons, hadrons, and quarks. These 5 pillars are where the bulk of your particle physics marks are hiding. Section 1. Rutherford's nuclear model. This is where we establish the absolute baseline of matter, and where a lot of students make their first critical errors. Okay, look at the setup. This is Rutherford's famous 1911 alpha particles scattering experiment. We are firing a beam of positively charged alpha particles at a microscopic sheet of gold foil. Now, let me introduce you to 2 types of students I see all the time. First, there's Alex. Alex looks at a question about this experiment and overloads the answer with raw physics facts, writing a massive, disorganized paragraph about everything Rutherford ever did. Zero analysis. Then there's Sam. Sam rushes, misses the command words like describe or explain, and just writes alpha particles bounced. Both of them are leaving huge marks on the table. When the Cambridge board asks you to analyze this experiment, they want to see you decode the data. The data here is that the vast majority of particles pass straight through with virtually no deflection, but a tiny fraction deflect wildly, some even bouncing straight back. So how do we pitch the perfect answer? We use the Peel framework, point, evidence, explanation, link. Your point? The atom is mostly empty space. Your evidence? The fact that almost every single alpha particle went straight through the gold foil. That's your explanation and link right there. But what about that tiny fraction that bounced back? That 1 in 10,000 extreme deflection? You cannot just say it hit something. You need to explicitly state that the alpha particle collided with a massively heavy, densely packed, and positively charged center. Because alpha particles are positive and like charges repel, that extreme deflection is the ultimate proof of a dense positive nucleus. Boom, full marks. You've justified your conclusion with the physical evidence. Moving on to Section 2, subatomic particles and isotopes. We are opening up that tiny nucleus to see exactly what lives inside, and more importantly, how the exam board wants you to talk about it. Before we continue, subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's look at this data table. This is exactly the kind of complex physics data source you'll need to scan in your exam. We're comparing protons, neutrons, and electrons. Look at the mass column, measured in unified atomic mass units. Protons and neutrons sit at roughly 1, but the electron, it's almost 2,000 times lighter, specifically 1 over 1840. If a question asks you to compare the mass distribution of an atom, do not be like Sam and just say electrons are light. Use the data. State that the nucleus contains virtually all the mass of the atom, despite taking up almost none of the actual volume. That level of precision is what separates an A from an A star. Now we hit a classic Cambridge trap, terminology. Nucleon number versus proton number. The proton number is the absolute strict identity of an element. Change the protons, you change the element. But what happens if we change the neutrons? We get an isotope. If the command word on your paper is define isotope, I guarantee you Alex is going to write a rambling paragraph. The board wants a crisp, data-driven definition. Isotopes are atoms of the same element with the same number of protons, but a different number of neutrons. That's it. It's precise, it's accurate, and it locks in the points. Here is how that plays out in standard notation, using chlorine-37 as our example. The bottom number, 17, is your proton number. The top number, 37, is your nucleon number. That's the total of protons plus neutrons. A massive point students miss here is chemical properties. The exam might ask why chlorine-35 and chlorine-37 react exactly the same way. The winning strategy? State that because the proton number is completely unchanged, the number of orbiting electrons remains exactly the same. And since electrons govern chemistry, the chemical properties are identical. You've provided the evidence, and you've linked it to the outcome. Section 3. Understanding radioactive decay. This is where things get dynamic and where your time management matrix in the exam becomes absolutely critical. You are going to see a table like this in your paper. We are comparing the nature, charge, and penetration levels of alpha, beta minus, beta plus, and gamma radiation. When densely packed nuclei are unstable, they shed energy through decay. Let's decode this efficiently. Alpha is heavy. It's a helium nucleus with a +2 charge. Because it's heavy and highly charged, it ionizes everything it touches, losing energy rapidly, meaning it's stopped by mere paper. Beta particles are fast-moving electrons or positrons. They penetrate further, needing millimeters of aluminum to stop them. And gamma? Zero mass, zero charge, just pure, high-energy electromagnetic radiation that needs centimeters of dense lead to even slow it down. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Section 4. The Neutrino Mystery. This right here is one of the most historically significant scientific detective stories and a prime candidate for a high-mark explanation question. Welcome to our interactive workshop. I'm putting a 60-second visual timer on the clock in my mind for you to process this graph. This is challenge 1, data scan. Look at the energy spectra comparing alpha and beta emission. On the left, alpha particles have specific, sharp, discrete energy peaks. But look at the beta particles on the right. This is a continuous, smeared-out curve. They're flying out with a whole random range of energies. If you're pitching this to the board, you need to highlight this exact discrepancy. Alpha is discrete, beta is continuous. Now for challenge 2. Find the flaw. I want you to imagine a student writing this sentence in their exam. Beta particles have a continuous energy spectrum because energy is not always conserved in quantum physics. Did you spot the flaw? It's a massive red flag. Energy must be conserved. The board will give you 0 marks for breaking a fundamental law of physics. If the nucleus drops from a specific high-energy state to a specific low-energy state, it releases a very set amount of energy. So if the beta particle is only carrying away a random fraction of it, where on Earth is the rest of the energy going? The equation simply doesn't balance. Here is your green checkmark top-tier answer. The missing puzzle piece is the neutrino. To save the law of conservation of energy, physicists realize that the beta particle doesn't fly out alone. It has a tiny, invisible, ghost-like partner. This neutrino has no charge and virtually no rest mass, meaning it's practically undetectable. But it secretly shares the available energy. If the beta particle takes a little, the neutrino takes the rest. This perfectly explains the continuous curve. Writing this explicitly shows the examiner you understand both the data and the underlying conservation laws. Section 5. Leptons, hadrons, and quarks. We are zooming in one final time to completely blow apart everything we thought we knew about protons and neutrons. Let's establish our final system of definitions. The subatomic world is split into 2 distinct camps. You need to be able to contrast these instantly. Leptons are your true fundamental particles. They have absolutely no internal structure. Electrons at our ghostly neutrinos, they are leptons. They cannot be broken down further. Hadrons, on the other hand, are the heavyweights, like protons and neutrons. For a long time, we thought they were fundamental, but they aren't. Hadrons actually have a hidden internal structure. They are made of smaller puzzle pieces. And what are those smaller puzzle pieces? Quarks, fundamental particles with incredibly bizarre names. Physicists call these different types flavors. We have up, down, charm, strange, top, and bottom. Now, for the Cambridge syllabus and for everyday matter that makes up the entire macroscopic world around you, we really only care about the up and down quarks. Challenge 3, speed writing. You have 30 seconds to write a perfect peel paragraph explaining the charge of a proton using its quark structure. Go. Here's what you should have written. Point. A proton is composed of 2 up quarks and 1 down quark. Evidence. An up quark has a fractional charge of +2/3 and a down quark is -1/3. Explanation. Adding +2/3, +2/3, and -1/3 mathematically equals exactly +1. Link. Therefore, the internal quark structure perfectly accounts for the overall positive charge of the proton. If you follow that framework, you are literally guaranteeing yourself top marks. The neutron works the exact same way. 1 up and 2 downs equals a net charge of exactly 0. Now, let's tie the entire system together. This is your 100% mark potential concept. When we talked about beta minus decay earlier, we said a neutron magically turns into a proton and spits out an electron. But now we know the truth. Beta decay is actually just a tiny quark changing flavor deep inside the hadron. A single down quark converts into an up quark. When it does this, to conserve both charge and energy, it has to release an electron and an antineutrino. This isn't just memorization. This is understanding the fundamental source code of the universe rewriting itself. If you explain beta decay in terms of quark flavor changes on your A-level paper, the examiner knows they're dealing with a top-tier candidate.
I want to share this humbling thought from the source material. It reminds us that things on the nuclear and subnuclear scale behave quite differently, and we have absolutely no right to expect them to behave in the same way as things in our everyday world. They don't behave like footballs or planets or anything intuitive. This is quantum physics. You have to trust the data, apply the strategic frameworks we've discussed today, and decode what the universe is actually telling you.
Think about it. If the solid world around us is entirely constructed from these tiny, flavor-shifting quarks and ghostly neutrinos streaming through us by the billions, what else about our universe is hiding in plain sight? Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. I'll see you in the next strategy session.